Hello and welcome to our fifth lecture on EE274 COE197E. For today, we'll discuss Z-transform for discrete time systems. So first, I'll introduce the complex exponential Z, and then we'll go with the transform definition as well as some examples. And then we'll see the region of convergence and its properties. And last but not the least, we'll discuss some of the operations and properties in the Z domain. In our previous lectures, we've seen that most of the signals can be represented by a complex exponential of the form z to the n or re to the j omega n, as we've solved in the natural responses and forced responses of our systems. Shown here are examples showing that this particular form for our complex exponential can cover most of our signals. If z is a positive number greater than 1, then we'll have an exponentially increasing signal. If z is less than 1 and a negative value, we'll have an exponentially decreasing and an oscillating signal. Now for cosines, we can use Euler's representation to represent it in the form re to the j omega n. And here we still have a periodic and oscillating signal. And if z is 1, we'll just have a constant value. Let's consider a discrete time system with our generalized complex exponential input. We know that to get y of n, we need to convolve our x of n with the impulse response of the system. And by using the convolution formula, we can have this summation of h of k, x of n minus k, from negative infinity to positive infinity. Plugging in our input, we'll have a summation of h of k, z to the n minus k, from negative infinity to infinity. We can isolate z to the n, and here we have our output, which is still a complex exponential, but just scaled by a factor h of z. We can say that in the perspective of z, the discrete time convolution just becomes multiplication. Again, we've seen that the output for our system is still a complex exponential, but with the same frequency. And the output is just scaled by a factor h of z. And this h of z is what we define as the z-transform of our impulse function. Now let's try to apply the z-transform definition to the following signals. For x1, plugging in the formula, we'll just have a summation from n equals 0 to n equals 4, since it's a finite sequence. Then expanding the summation, we'll have 5 terms. And we'll get this polynomial in z. Taking a closer look, we can see that we have z to the minus 1, z to the minus 2, z to the minus 3, and z to the minus 4 terms, which means that this polynomial must not have a value for z equals 0. Applying the formula for our x2, we'll get this summation. And what we see here is a form similar to a geometric sequence. And getting the sum of this sequence, we'll have 1 over 1 minus az to the minus 1. And for the convergence of this function, we need the common ratio to be less than 1. And rearranging this, we'll get the absolute value of z should be greater than the absolute value of a. For our third example, we have an anti-causal signal. So we'll have a summation from negative infinity to negative 1. Here we can still get the same function, although the common ratio condition will be different. Here we'll have the magnitude of z should be less than the magnitude of a. So what can we learn from these examples? Now, the z-transform is usually a rational expression in terms of z, or z to the minus 1. And the expression for x of z is usually accompanied by a restriction of value, which we call the region of convergence. In our x2 and x3, we'll see that they both have the same form, and one thing that distinguishes them from each other is the ROC. So we can see that the complete z-domain representation of our signal should include the expression as well as the region of convergence. Shown here are the z-transforms for our common signals. For our delta of n, it's just 1 in the z-domain. For our unit step, we have 1 over 1 minus z to the minus 1. For exponential signals, we have 1 over 1 minus az to the minus 1. We also have both the causal and anticausal forms. We have the ramp functions, and we also have our sinusoidal functions. The ROC dictates the convergence of our z-transform. And since our complex exponential z is re to the j omega, then we'll have circular regions which are affected by the magnitude of r at different omega. So we can plot this z in a complex plane as shown here. Now going back to our previous examples, so once we get our z-transform, we can rearrange it as a rational expression, and then here we'll try to get the roots of our numerator and denominator called the zeros and the poles respectively. For x1, we'll have 4 zeros denoted by the circles and 4 poles at z equals 0 denoted by the x. Now our ROC dictates that we can have all values of z except at z equals 0 or at the pole location. So in this plane, we can have all the values of z except for the value at the pole. For x2, we can also express it as a rational expression, z over z minus a. We'll have a 0 at 0 and a pole at a. And since the ROC condition should be the magnitude of z greater than the magnitude of a, then we'll have a region that should be outside a circle with radius a. So here is the range of the ROC. For our x3, we also have the similar function but with a different ROC. Here we have the magnitude of z less than the magnitude of a, which means we're now taking a look at the interior of the circle defined by z equals a. Let's go to some properties of the ROC. First, the ROC of x of z should consist of a ring in the z-plane centered around the origin. Among the 3 figures, only the third figure is a valid ROC. Next, the ROC should not contain any poles. If we have this donut-shaped region as our ROC, then the pole should not be inside this region, as shown here on the left. Third, the ROC is a connected or a single contiguous region, which means it can only be a donut shape, a circle, or a region outside the circle. If our signal is of finite duration, then the ROC will be the entire z-plane with the possible exception at z equals 0 or z equals infinity, which depends on the causality. Shown here are 3 examples. So for x1, if we have an anticausal signal, we'll have exception at z equals infinity. For x2, we have a causal signal, so we'll get an exception at z equals 0. For x3, we have a two-sided signal, so we'll get exceptions at z equals 0 and z equals infinity. For infinite sequences, if x of n is right-sided, then the ROC is outside the circle defined by the pole. If x of n is a left-sided sequence, then the ROC should be within the circle defined by the pole. And if x of n is two-sided, then we'll have a ring in the z-plane, as shown in this figure. Now let's proceed with the discrete time operations in the z-domain. First, we have linearity. If we have a1x1 of n plus a2x2 of n, then it follows that the transform should be a1x1 of z plus a2x2 of z. Here, the ROC should be the intersection of the ROC of x1 and the ROC of x2. We also have time shifting. So if we have a time delay by k, then we multiply the transform by z to the minus k. And if we have z to the minus k, we have exception at z equals 0. Now, if this time shift is an advance, then we multiply z to the k, and then we'll have exception at z equals infinity. If we have our input enveloped by an exponential signal, a to the n, then we'll just multiply a to the minus 1 to our z. And the ROC will also get scaled by the magnitude of a. We also have these following properties for differentiation, conjugation, the real and imaginary parts. For folding, we'll just invert the z, and we also invert the ROC. And for convolution, we've already shown that it just becomes multiplication in our z domain. Similar with the linearity property, the ROC should be the intersection of the individual ROCs. And last but not the least, we have the initial value theorem, which states that the value at x of n equals 0 will be approximated by the limit of x of z as z approaches infinity. Now, some notes on linearity and convolution. So applying the operation will lead to an ROC which is the intersection of the individual ROCs. Now, if the operation yields a finite duration sequence, then the ROC will also change. However, if there is no intersection on the ROCs, then we say that the Z transform does not exist or that there is no Z transform. Now let's determine the Z transform of the following sequence. Here we have a causal part and an anti-causal part. And for the causal part, we'll have the property a to the n u of n, which becomes 1 over 1 minus az to the minus 1. Here, a is equal to 1/2. And for the anti-causal part, we have the property minus a to the n u of minus n minus 1, which also becomes 1 over 1 minus az to the minus 1. And here, the value of our a is 2. So we'll have this following function. And since this is a linear combination of two sequences, then we'll get the intersection for the ROCs. For the causal part, we have magnitude of z greater than 1/2. And for the anti-causal, we have the magnitude of z less than 2. Suppose we change the poles of each component. So if we have 2 to the n u of n plus 1/2 to the n u of minus n minus 1, then we'll see that there is no intersection of the ROCs. That particular case will lead to a non-existent Z transform. In this next example, we need to determine the Z transform of the time-shifted signal. So we have 2 to the n u of n plus 3. We already know the property a to the n u of n. Now, if we are to use the time-shifting property, we need to express all the arguments of n with a time shift. We need to represent this equation as 2 to the minus 3 times 2 to the n plus 3 u of n plus 3. This particular term, we can derive the property as z cubed over 1 minus 2z to the minus 1. And then we'll just incorporate the 2 to the minus 3. And then we'll get our Z transform. The ROC for this will still be the same with the exception at z equals infinity because of the time advance. For our last example, we need to convolve these two signals using Z transform. So for x of n and w of n, we can already derive the Z transforms for each, as shown here. Using the convolution property, we just need to multiply these two functions, and then we'll get this one. And luckily in our table, we see some properties which allows us to invert this back in time, as shown here. So we'll get n 3 to the n plus 1 u of n. In summary, we've discussed the Z-transform, which is a useful tool that we can use to analyze our discrete time signals and systems in a new domain. And this particular transform is accompanied by what we call the region of convergence, and it guarantees the existence of our transforms. And lastly, we've also shown some of the properties and operations that we can use later in solving our system responses. For further reading, and recommend these following chapters in our references. And that's it. Thanks for listening.